Physics carries a quiet idea. Disorder is easier than order. Most of the time that means coffee cools, ice melts, and tidy rooms fall apart. Extend that same rule across enough time, and it leads somewhere strange. In some cosmological models, statistics favor a single mind, complete with vivid memories and a convincing sense of reality, appearing by accident over an entire universe like ours with a real past. Physicists call that hypothetical mind a Boltzmann brain. Tonight, we will trace how an ordinary idea from thermodynamics becomes one of the strangest stress tests in modern cosmology. Physics has not proved that your memories are fake. But if a theory makes fake observers more common than ordinary ones, that may be a sign the theory itself has gone wrong. To see where this comes from, we only need one basic intuition. In a system left alone, messy arrangements outnumber tidy ones by an absurd margin. That is the heart of entropy. If a system sits near equilibrium for a very long time, small random departures from that equilibrium are far more likely than large ones. A sock might land on a chair by accident. An entire room will not clean itself. A few Scrabble tiles might form a word. They will not produce a full page of coherent text. That difference matters. If nature draws random fluctuations from a mostly featureless state, then a small island of order costs less than a vast one. A single observer-like structure, just complex enough to have thoughts and impressions, is a much smaller request than a universe filled with galaxies, stars, planets, biology, and billions of years of history. So what is a Boltzmann brain? In plain language, it is a self-aware physical system that appears as a rare fluctuation instead of emerging from an ordinary cosmic history. It is not a mystical soul or a computer simulation. It is matter arranged by chance into a brief observer. The disturbing part comes next. If that arrangement encoded sensations, memories, and a sense of personal continuity, then from the inside it could feel normal. It could seem to remember a childhood, a planet, a night sky, even the beginning of this sentence, though none of that had happened. The key distinction is simple. One mind sits inside a long causal story. The other only imitates the evidence inside a single mind for a moment. This idea has older roots. Ludwig Boltzmann and others were trying to explain the arrow of time. Why the universe moves from lower entropy to higher entropy, and why the past looks more ordered than the future. One tempting answer said the larger universe might usually sit in equilibrium, while we happen to live inside a rare fluctuation away from it. First, that sounds clever. It uses the same statistical logic that works in thermodynamics. That logic carries a trap. If fluctuations do the explanatory work, then the most likely fluctuation is not an entire rich universe with a genuine 13.8 billion year history. It is the smallest fluctuation that matches what seems to be observed. Follow that reasoning far enough, and it pulls you away from a vast real cosmos toward a tiny counterfeit patch of order, or in the limit, a single mind with a fabricated past. This is where our own experience starts to matter. We do not only feel that the world has a past. We see layer after layer of evidence that points to one. Light from distant galaxies carries a record of cosmic expansion. Rocks preserve ancient climates. Fossils fit into evolutionary history. Atoms, stars, planets, and living systems sit inside one long lawful chain of causes. That richness matters because a Boltzmann brain is a shortcut. It gives you the appearance of evidence without the full machinery that would produce it. So the first reaction is obvious. Surely we are not Boltzmann brains. As a practical judgment about our world, that reaction is strong. But the paradox is not about private intuition. It is about typicality. If a theory says observers with our kind of evidence usually appear by accident, then the theory is in trouble even if our world feels solid and consistent. This is where the idea stops sounding like a spooky party trick and starts to matter in cosmology. The question is not, are you secretly a Boltzmann brain? The question is, what does a theory predict for a typical observer? If a model of the universe produces ordinary observers only rarely, but allows vast numbers of isolated accidental minds with convincing false memories, that model has a problem. Under that theory, an observer with your evidence would usually not belong to a long cosmic history. It would usually be a brief fluctuation that only seems to remember one. That creates more than discomfort. It threatens scientific trust. If a theory says most observers who see a lawful universe are deluded by construction, it starts to undercut the reasoning physicists use to accept it. Physicists sometimes call this cognitive instability. In plain language, a theory becomes hard to trust if it says minds like ours are usually accidents with fake pasts. Boltzmann brains matter because they work as a stress test. They ask whether a cosmological model produces reliable observers in a reliable world, or only the appearance of one for a moment. Where does this become more than a philosophical headache? In many versions of modern cosmology, it happens in the far future. If the universe keeps expanding under something like a positive cosmological constant, it can drift toward a de Sitter-like state. That sounds technical, but the picture is simple. Space grows emptier, quieter, and more isolated. Distant galaxies fade beyond a cosmic horizon. Yet for a local observer, that horizon still matters. It carries entropy and a tiny temperature-like character. In other words, even an almost empty universe can still follow a thermodynamic story. If that state lasts for absurdly long stretches of time, rare events start to matter. They do not become likely in any ordinary sense. The point is that the clock never stops. That is why Boltzmann brains entered serious cosmology. A long-lived, nearly empty universe may look uneventful, but if it has horizon thermodynamics and enough time, the old fluctuation logic returns. The worry is that ordinary observers appear during a brief era of stars, planets, chemistry, and biology, while accidental observers keep accumulating in the silent dark long after that era ends. Then the problem gets bigger. In eternal inflation and other multiverse-style pictures, space does not only last a long time, it may produce enormous, perhaps infinite amounts of space-time. Different regions can end up with different local conditions, while inflation keeps creating more room elsewhere. At that point, the question is no longer only, can Boltzmann brains happen? It becomes, how do we count observers in a universe that never stops making new places? This is the measure problem. If there are infinitely many ordinary observers and infinitely many Boltzmann brains, simple totals tell you nothing. You need a rule that turns that infinity into something comparable. Different rules can give different answers. Under one measure, ordinary observers may dominate. Under another, Boltzmann brains pile up at late times. So the paradox starts doing real work. It shows that some cosmological frameworks are hard to interpret cleanly. If your prediction changes too much when you change the counting rule, then the theory has not yet told you in a stable way what a typical observer should expect to see. At this point, it would be easy to leave the story in existential fog. But physicists do have responses. One is simple. If a model predicts Boltzmann brain domination, reject the model. Treat that result as a sign that the theory, or the way physicists interpret it, has failed a basic consistency test. Another possibility is vacuum decay. If the de Sitter-like phase is temporary, and the vacuum changes state before enough accidental observers can build up, then the problem may never become dominant. This is model building, not apocalypse language. The question is whether the universe's late-time state lasts long enough for these rare fluctuations to overwhelm ordinary observers statistically. There is also a deeper challenge to the standard argument itself. Some researchers, including Boddy, Carroll, and Pollack, argue that physicists should not picture a stationary de Sitter vacuum as constantly producing real observers out of noise. In that view, a thermal-looking vacuum is not the same as a stream of actual events. If that is right, the Boltzmann brain threat is less automatic than earlier discussions assumed. But that point is still debated. It turns on difficult questions about quantum states and what counts as a real fluctuation at all. We end where we began. Disorder is easier than order. But the real mystery is not whether one lonely mind could flicker into existence. It is why our universe seems to offer something richer. A deep past, a lawful world, and records that agree with one another across billions of years. That is what Boltzmann brains test. Any cosmology that makes brief fake observers more typical than ordinary ones is, at the least, incomplete. And that leaves one final question. What kind of universe can produce observers who are not only conscious for a moment, but connected to a real history? If you want more of this kind of quiet deep space thinking, you can like the video and subscribe. We end with the same quiet rule we started with. Disorder is easier than order. That is not the mystery. The mystery is what kind of universe can still produce observers whose memories connect to a real history. Boltzmann brains matter because they test that point. If a cosmological model says the most likely observer is a short-lived mind with a convincing but invented past, the model has a problem. Maybe the late universe does not fluctuate the way this simple story assumes. Maybe the way physicists count observers in huge cosmologies points them in the wrong direction. Maybe a de Sitter-like phase ends before that outcome can take over. And some modern arguments, including work by Body, Carroll, and Pollock, suggest a stationary vacuum may not produce the kind of time-dependent observer events this paradox seems to require. So the question is not whether your memories are fake. The question is whether our best theories can explain a cosmos with stars, planets, records, other minds, and a deep past you can trust. If you'd like more calm explorations like this, you can subscribe.